Good afternoon, students. The last class we completed vapor prayer of liquid in liquid, no? Vapor prayer of liquid in liquid we did, and the composition of liquid in vapor phase, one numerical also we completed. Correct? Once recollect, vapor prayer of liquid, and both the liquids are volatile, I thought you. In that we studied Raoult's law. Now today we will discuss vapor prayer of solid in liquid. Right heading, vapor prayer of solid in liquid. Right, today's date, right heading, vapor prayer of solid in liquid. Right heading, vapor prayer of solid dissolved in liquid. Now observe here. In the last class we discussed vapor prayer of liquid in liquid. No, now see, this solid is non-volatile. What is meant by non-volatile, student? The one that cannot convert into vapor. Such substance we call non-volatile. Like what? Urea, glucose, sucrose. So this non-volatile will be generally what? Urea. Last class we discussed sucrose, glucose. These are all non-volatile. No? Now observe here. Here Raoult, what is the name of the scientist? Raoult's law. We discussed in the last class, recollect Raoult's law. Now very important, what Raoult's law said, the vapor pressure of a solution containing non-volatile solute, like what? Urea, sucrose, glucose, is directly proportional to mole fraction of its solvent. Because here solvent is only volatile, whereas solute is what, student? Non-volatile, no? So vapor pressure of a solution containing a non-volatile solute will be directly proportional to mole fraction of its solvent. That is what, which one? Liquid, no? Which is solvent here? Liquid is volatile. So that was the statement given by whom? Raoult's law. So write a statement, the vapor pressure of a solution. Are you following, all of you? So the vapor pressure of a solution containing non-volatile solute is directly proportional to mole fraction of what, student? Solvent. Is directly proportional to mole fraction of its solvent. This was the statement given by whom? Raoult. Clear? All understood, all of you? Why? Because solvent is the only volatile component. Copy this statement, and this relation is called Raoult's law. Clear? Now mathematically how we represent this? See, the vapor pressure of the solution, that is PS, this is vapor pressure of solution containing non-volatile solute, is directly proportional to mole fraction of its solvent. That is chi. Chi is what? Mole fraction of solvent. Now removing the proportionality, what we write, student? Vapor pressure of solution is equal to P naught. What is P naught? Vapor pressure of pure solvent into mole fraction of solvent. This was the relation given by Raoult. Very important relation. Keep it in box. Where PS is vapor pressure of solution. What is P naught? Vapor pressure of pure solvent. And what is chi? Mole fraction of solvent. Clear, students? Understood? And very important in exam, they ask questions numericals from Raoult's law. Yesterday we studied vapor pressure of liquid in liquid. This is vapor pressure of solid of non-volatile dissolved in liquid. Clear? Copied? Everyone copied? Understood? Right. Now let us draw the graph between vapor pressure versus mole fraction. Copied? Understood now everyone? Right. Now see, next I am showing you the next one. See, graph we draw. Draw graph two extremes. You draw the graph between two extremes. This y-axis you take vapor pressure, and here you take chi. What is chi? Mole fraction. And this extreme, mole fraction of A comes to be 1. As we go like this, mole fraction of A comes to be 0. And as you know, chi A plus chi B, here mole fraction of B comes to be 0. Here mole fraction of B comes to be 1. Now, what is that relation? Vapor pressure of pure solvent. Only for solvent we get here. Why? Because solvent is only volatile. Correct? That means P. Here what should I write? P naught. That is vapor pressure of pure solvent. And what happens to vapor pressure of pure solvent? It slowly decreases. See, because due to decrease in mole fraction of solvent. Whereas for solute we are not drawing. Why we are not taking solute, student? Because solute is non-volatile. Previously for liquid we got two graphs. Recollect. For two liquids are volatile, we drawn two graphs, but here we get only for solvent. This is vapor pressure of solvent. Getting idea? Only one graph we are getting here. See, this is vapor pressure of the pure solvent graph. Whereas for solute we are not drawing. Why? Solute is what type? Non-volatile. Understood, students? So this is the graph. See, for pure, this is the graph of vapor pressure of solid in liquid. Clear? Now write one question related to this vapor pressure of solid in liquid. Copied all of you this one. Now write one question on this. Say, write a question in the relation with 30 grams of urea is present in 45 grams of water at a particular temperature. And its vapor pressure of pure solvent for water is 300 mmHg. This is vapor pressure of pure solvent water given 300 mmHg. Then find the vapor pressure of solution. This is the question related on Raoult's law. See, so write the data. What he has given 30 grams of urea. This is solute. What type of solute, student? This is non-volatile solute. This is present in 45 grams of water is saying. So solvent is water, and water pure solvent vapor pressure given 300 mmHg. Then what will be the vapor pressure of the solution? So according to Raoult's law, what is the relation, student? We wrote vapor pressure of solution is equal to vapor pressure of pure solvent into mole fraction of what should we take? Solvent, no? Why? Because solvent is only volatile. Now had he given P naught to you, yes, P naught is given 300. And mole fraction of solvent, how you get mole fraction? You studied in the beginning, introduction. Number of moles of water by number of moles of water plus number of moles of water, urea. Correct? Mole fraction, recollect. Those who are revising, I told you on the day what we teach, recollect all this. This is mole fraction, how we write. Number of moles of urea by number of moles of urea plus number of moles of water. Up to this understood? Now in the question, had he given moles to you directly? No, given, no, mass given. Now copy this up to this, I write here. Then what we write? 300 into, what is the mass of urea? 30. And urea formula you have to know. What is the formula of urea? NH2CO NH2. When you find the molar mass of this, it comes 60. Algebraic sum you add, check 60 you get. That means what should I do? 30 by 60 upon 30 by 60 plus what is the mass of water given? 45 grams given. So 45, what is the molar mass of water? 18. Understood? This is how we get vapor pressure of solution. Now tell me, this vapor pressure of solution is equal to, any cancellation, 30 will cancel 60 by 2 times. This cancels by 1 by 2. This will cancel by 1 by 2. And 3 multiple will cancel. 3 6 are 18. 3 15s are. 3 2s are. 3 5s are. Correct? So finally what we are getting? 300 into 1 by 2 upon 1 by 2 plus 5 by 2. Copy this and find out. I am writing here, finally see PS is equal to 300 into 1 by 2 by 1 by 2 plus 5 by 2. And take LCM. What will be the answer? 300 into 1 by 2. LCM for this will be 2, no? So this will be 2 ones are 1 plus. This will be how much? 2 ones are 1, 5. So that comes how much, student? 300 into PS is equal to 300 into this 1 into 2 by 2 into 7. 6, you know, this is 6. $300 into 1 into 2 by 2 into 6. Now any cancellation, 2 to cancel, 3 hundreds are, 3 twos are. So this comes how much? 50. Check, vapor pressure of solution is coming 50. Check, student, answer should come 60. What should be the unit? mm of Hg. What is mm? Millimeter of Hg. So I have done wrong. Why I have taken 30 C? Mole fraction of water we have to take, no students. Here 30 I have taken urea. It's not urea. Mole fraction of solvent we have to take. So instead of 30 by 60, what you take here, see mole fraction of water we have to consider. Amma. Understood, Amma? I have taken mole fraction of solute I took. Now see actually what we have to take water, no? That is 45 upon 18 by 45 upon 18 plus 30 upon 60. Make correction. See what I did mistake. See here we have to take mole fraction of solvent we have to take, but not solute, no, because solute is non-volatile. Understood, friends? So see here what I did mistake. 30 grams I have to cut, not 30. You have to take solvent mass. You have to take because solvent is volatile, no. Now any cancellation 3 6 are 3 15s are 3 5s are 3 2s are. This is 5 by 2. This is 5 by 2. This comes how much? 1 by 2. Copy it, student. Now I write here 3. This can be written. Final tell what will be the answer. I am writing here 300 into 5 by 2 by 5 by 2 plus 1 by 2, students. So that comes 300 into 5 by 2. What is the LCM for this? 2, no? So 2 ones are 5 plus 1, 6 by 2. Finally, how much you get? Check. Here I am writing. So 300 into, this comes 300 into 300 into 300 into 2, 300 into 2 by 2 into 6, 300 into 2 by 2 by 6. Is it coming same? 3 ones are, these are 50. Why I am getting the same answer? Done this, see, I write it in next page. The next one. What is that we got? PS is equal to P naught into mole fraction of solvent, no? P naught how much he has given? 300. What is the weight of water? 45 grams, no? 45 upon 18 by 45 upon 18 plus 30 upon 60. So 3 multiple 3 6, 3 15, 3 2, 3 5. Correct. This is 5 by 2. This is 5 by 2. This comes 1 by 2. So this can be written 300 into 5 by 2 by 5 by 2 plus 1 by 2 amount. So this comes how much, student? 300 into 5 by 2. LCM will be 2 only, no? 1 2 1 1 5 2 1 1 6 by 2. So 300 into 5 into 2 by 2 into 6. 2 2 cancel. This comes 1500 by 6 amount. That means 3 2s are 3 500s are 2 will cancel by 250. You should get 250 mmHg. Check on me. So answer should be vapor pressure of solution should be 250 mm of Hg. Clear? This was previously what we did mistake. See, I took the mass mole fraction of solute I took. See here mole fraction of solvent we have to take. So final answer, check on all of you. Final answer should come 250 mm of Hg. This is the vapor pressure of solution. Clear? Understood? This is from Raoult's law, vapor pressure of solid in liquid, and solid is what? Non-volatile. Done. Understood, friends? See, now I show you the PPT of this. This is determination of mole fraction in vapor phase we did yesterday. And mole fraction of liquid phase, this is mole fraction of liquid phase yesterday we did. And see this one, Raoult's law. Now write next heading, ideal solution. Here with this vapor prayer of liquid in liquid we did, liquid solid in liquid we did. Now write heading, ideal solution. Write heading, ideal solution. Now what is ideal solution? See, a solution which obeys Raoult's law at all concentration is called ideal solution. So which one do we call ideal solution, students? A solution that obeys Raoult's law at all concentration is called ideal solution, just like ideal gas. You remember in states of matter, first year you studied a solution that obeys, write the statement. Solution which obeys Raoult's law. Raoult's law at all concentrations. He is known as ideal solution. Such solution what we call an ideal solution. Understood? So the solution that obeys Raoult's law at all concentration is called ideal. But none of the solution is to be ideal. That means most of the solution deviate from what? Ideal. That's what you remember. In states of matter also we studied real gas. So then what is meant by non-ideal? Non-ideal means what? A solution that do not obey Raoult's law at all concentration is called non-ideal solution. So what we define for this? Solution which do not obey Raoult's law. At all concentrations. He is known as what? Non-ideal solution. But most of the solutions will deviate from what? Ideal solution. Understood? Copy this. So first we discuss ideal, then we go for deviation from ideal. Understood, friends? Till now what I thought, vapor prayer of liquid in liquid we did. Understood, everyone? And vapor prayer of solid in liquid we did. Now next our discussion will be on ideal solution. So what is ideal solution? Simple, a solution which obeys Raoult's law at all concentration. But non-ideal means most of the solutions deviate from ideal. So first we discuss ideal solution. Copied, everyone? Now we discuss ideal too. Now make two columns, one for ideal, one for non-ideal. In the page you make two columns. First column write ideal solution. Second column you write non-ideal solution or deviation from ideal. Understand? Now let us discuss one by one. Now see, in case of ideal solution, what we can say, it obeys Raoult's law, no? So here you write it obeys Raoult's law. Getting idea? It obeys Raoult's law at all concentration. Are you following, students? At all concentration, if it is obeying Raoult's law, it is called ideal solution. Now observe here. Let us take two liquids. Let us assume this is A liquid, this is B liquid. I am mixing A liquid with B liquid. So what happens? There will be interaction between what liquid and A, what liquid A and B, no? So after mixing A liquid with B liquid, the interaction among A and B will be same as in the pure state. Means initially how the interactions are there in the pure state A liquid, in the B liquid, after mixing also the interaction comes to be what? Same. In case of what? Ideal solution. So here make a note. Interaction between, are you getting my point? Interaction between A liquid and B liquid will be same as A liquid and BB liquid. Understood? After mixing, what happens to interaction A liquid, B liquid when I am mixing? The interaction of AB liquid, or I say AB liquid, will be same as what? A liquid and BB liquid. So here write interaction between AB liquid will be similar to what and what? Will be same as A liquid and BB liquid. Will be similar as liquid A and liquid B. Understood, student? Liquid A and B liquid. So as interactions are same, so there is no deviation. Understood? So interaction between liquid A when I am mixing with liquid B, it will be same as it is in what? Pure state, A liquid and BB liquid. Now see, coming to the next point, then how should be shape, size and character? The size, shape and character should be same as in what? A and B should have similar size, shape and character. Then only interactions will be same. Are you getting my point? So what we can write? Size. How should be size, student? Shape. How should be shape? Size, shape and character. Should be how, student? Should be same or differ? Should be same, no? Size, shape and character should be same. Then only interactions come same. Are you following? So the size should be similar, the shape should be similar, character should be similar. Then interactions comes what? Same, no? So make a note. Size, shape and character should be same. Now coming to the next point. Now tell me, students, what will be volume change of mixing? Suppose 50 ml of A liquid, 50 ml of B liquid I have added. Assume 50 ml from A, 50 ml of B I added. Will it be exactly 100 ml or not? That means neither increase in volume nor decrease in volume. Means what is the change in volume? 0. Why it is coming 0? Because interactions are same, no? So volume change of mixing will be how? Volume changing of mixing will be 0. Why there is 0? Since there is neither attraction nor repulsion, because interactions are coming same or not. Are you following? So volume change of mixing will be 0. Understood, all of you? Now coming to next point, say enthalpy. You know what is enthalpy? Heat change accompanied. Now tell me, will be there any exothermic or endothermic here? No. Why? Because interactions are same, no? So change in enthalpy. What is enthalpy? You remember it is shown with delta H. Change in enthalpy. Enthalpy of mixing will be how, student? 0. Why? Because there is neither heat is evolved nor heat is evolved. Since interactions are same, no? So enthalpy change of mixing is 0 since interactions are 0. Now tell me, when you are mixing two liquids, in thermodynamics, what happens to entropy? Entropy, randomness. Entropy of mixing will be greater than 0. Whenever you are mixing two liquids, what happens? Randomness increases, so entropy of the liquid increases. This will be common for all, whether it is ideal or non-ideal. And Gibbs free energy. What is Gibbs free energy? In thermodynamics, spontaneity of a reaction. So Gibbs free energy will be what? The Gibbs free energy will be less than 0. Means for the process to be spontaneous, how should be? Gibbs free energy should be negative, no? Then only process will be what? spontaneous. So Gibbs free energy change will be less than 0. Understood? So in exam they give you statements how should be volume change of mixing in ideal. Volume change of mixing will be 0 and enthalpy changing of mixing is 0. Entropy, whenever we are mixing two liquids, what happens? Randomness increases. This will be common in both the case, whether it is ideal or non-ideal. Gibbs free energy to be spontaneous, how it should be? Negative, no? So Gibbs free energy change will be less than 0. Up to this understood, copy that. Clear, understood? Huh? Now see, I am continuing here. Actually, we will write this in non-ideal or else I write in another page. Copied up here, now I write in next page. See. Now tell me students, what are the examples we can take for ideal? See, benzene. You know, benzene, 11th class organic you people studied. Benzene and toluene. How will be the shape and size similar, no? This will behave as what? Ideal. So in exam they ask you by giving example which is ideal. Size, shape should be same, no? And you know N-hexane. What is N-hexane? Normal hexane and N-heptane. Can I say they form ideal or not? Why? Because their size and shape is same, no? And you can take ethyl chloride and ethyl bromide. Will they behave as ideal or not? Because size of same, ethyl same, no? And can I take chlorobenzene, bromobenzene? Chlorobenzene, bromobenzene can come under what? Ideal. These are the examples for ideal. Copy these examples. And how will be vapor pressure of A component, student? Vapor pressure of A will be equal to P naught of A into chi A, no? There is no deviation, no? This we learned from Raoult's law. And how will be vapor pressure of B component? Vapor pressure of B component will be same as what we get experimentally. Theoretically also it will be same, no? And how will be total vapor pressure of the solution? Total vapor pressure will be equal to what? That is P naught of A chi A plus P naught of B chi B. There is no variation, no? Why? Interactions are same. So these are the examples for ideal, and these points you have to keep it in mind. Understood? So see, once again recap, copy this fast. These are the examples: benzene, toluene. What is the name of this compound? Toluene. This is example 2, this is example 3, this is example 4. What is this compound called? Chlorobenzene, bromobenzene. Clear, understood all of you? So this is what ideal. Copy them all of you. Now see, I show you the first beginning one. This is ideal. When do we call ideal? If the interaction between AB liquid is same as A liquid and BB liquid. How should be size, shape and character? Size, shape and character should be same. And what will be the volume change of mixing? Means there should be no change in volume because interactions are same. And what will be enthalpy change of mixing? Means heat neither is evolved nor evolved. Neither heat is absorbed nor heat is evolved. Means there is no interaction. And what will be the entropy change of mixing? Whenever we are mixing two liquids, randomness increases. So entropy increases greater than 0. What will be Gibbs free energy change of mixing? Means it will be less than 0 because to be spontaneous, delta G should be negative. Understood? And next see, and we wrote how should be partial pressure of A? Partial pressure of A, theoretically, experimentally, it will remain same because interactions are same. Partial pressure of B will be experimentally, theoretically, it will be same. There is no variation. And total vapor pressure of the solution will be sum of the partial pressure. There is no variation since interactions are same. And these are the examples that we can quote for ideal solution like benzene, toluene, N-hexane, N-heptane, ethyl chloride, ethyl bromide, chlorobenzene, bromobenzene. Up to this understood all of it. So this is what for ideal solution. Now we go for non-ideal. Clear, copied? Shall I proceed next? Now see, next coming to non-ideal solution. Now in this non-ideal we come across two cases. That means the deviation, positive deviation. This is showing positive deviation from Raoult's law. The another one is what? A negative deviation. So we divide this further into two categories. The non-ideal we are dividing into two categories. Then when do we call non-ideal? See, does it obey Raoult's law, student? Here, no, no. Do not obey Raoult's law. Do not obey Raoult's law. That means deviating from what, student? Raoult's. Following? Now observe here. Now assume liquid A I mix with liquid B. Now what happens? The interactions between liquid A, B after mixing becomes weaker. Means molecules are loosely held because interactions are weaker. So what happens? It will have more tendency to vaporize. That's the reason we are calling positive deviation. So how will be the interaction of A, B when I am mixing? Interaction of A, B liquid will be weaker compared to the pure state. So are you getting my point? Here we mentioned right here. Interaction between AB liquid, how it should be, student? Between AB liquid will be weaker, no? Weaker compared to whom? Pure state, compared to AA liquid and BB liquid. So after mixing, interactions comes what? Weaker. So that's the reason they are showing what? Positive deviation. Means they are loosely held. The molecules are loosely held after mixing the two liquids. Getting idea, all of you? Now tell me, how should be size, shape and character? It should differ, no? Then only deviation comes. Whereas in case of ideal, how it is size, shape and character? Same. So here write size, shape and character should differ. The size should differ, shape should differ and character should differ. Getting idea, all of you? Then only deviation comes. Should differ. Understood, student? Size, shape and character should differ. Now tell me, student, I have taken 50 ml of A liquid, 50 ml of B liquid and I have added. Actually it should come 100, no? But it is not coming 100. Since molecules are weaker, it is coming slightly more than 100, 100.1, 100.2. So what will be the total volume change of mixing? Will it be greater than 0 or less than 0? Since molecules are loosely held, no, weaker, so I am adding 50 ml of A, 50 ml of B. It is not coming exactly 100. Previously we got 100. Why? Because there is no interaction. Here the molecules are weakly held. So what will be volume change of mixing here? Will it be greater than 0? Do you agree, all of you? So volume change of mixing comes here greater than 0. That's what we are calling positive deviation. Why it is coming 0, student? Greater than 0. Why it is coming greater than 0? Because molecules are weakly held. Getting idea? Because molecules are loosely held, so volume comes slightly more than 100. Now what will be enthalpy change of mixing? Think over whether it is endothermic or exothermic. After mixing A liquid with B liquid, AB liquid becomes weaker. Means I am spending energy to break AA liquid and BB liquid. Breaking of bond is called endothermic, no? So enthalpy change of mixing will be what here? Greater than 0. Why? Because we have to break the bonds of A liquid, B liquid to form what liquid? AB liquid. Because AB interactions are coming weaker. That means interaction of A and A, B and B will be stronger. So what will be enthalpy change of mixing? Enthalpy change of mixing will be greater than 0. Understood why it is coming greater than 0? Because we are spending energy to break the bond. Enthalpy change of mixing is greater than 0. But these two will be common whether it is ideal or non-ideal. Why? When you are mixing two liquids, what happens to entropy? Entropy change of mixing will be greater than 0. Entropy change, whether it is ideal or non-ideal, students keep it in mind, these two will be common. Whereas Gibbs free change, Gibbs free energy also common. What to be and to be spontaneous, what should be the value of delta G? Delta G should be less than 0. So entropy should increase and Gibbs free energy should be less than 0. These two will be common for whether it is ideal or non-ideal. Up to this understood? So when do we get positive deviation? Interactions of AB becomes weaker compared to the pure liquid AA liquid and BB liquid. And how will be size, shape and character? They should differ. What will be the volume change of mixing? Volume change of mixing should come greater than 0. Why it is coming greater than 0? Because molecules are held loosely. And enthalpy of mixing will be endothermic. Why we have to spend energy to break A liquid and B liquid? And entropy change of mixing will be greater than 0. Gibbs free energy will also be less than 0. These two will be common, whether it is ideal or non-ideal. Clear all of you? Now see, we go into next one. See, and the next page I will write continuation. Now see, how should be experimental vapor pressure compared to theoretical? It is not equal. No. Why it is not equal? Because size, shape, they are varying. That means partial pressure of A, when I compare with Raoult's law, will it be greater than P naught of a chi A or not, student? The partial pressure of A, this is experimentally is coming more than what is theoretical. Deviation, no? And partial pressure of B also comes more compared to what Raoult's law, P naught of B into chi B. No, why? Because loosely held. And total pressure will also be greater than what, student? P naught of a chi A plus P naught of B chi B. Understood? There is variation, no? So total vapor, these are the variation because experimental is not equal to theoretical. Then what are the examples? See, keep it in mind, one key point, how to recognize. In exam they ask, which of the following is positive deviation? Where else hydrogen bond you are breaking? You know hydrogen bond in 11th class chemical bonding you people learned. By adding two liquids, if hydrogen bond breaks, then it comes under positive deviation. Example, you take ethyl alcohol. What is the formula of ethyl alcohol? C2H5OH. You mix with water. What happens? The interactions between ethyl alcohol will be broken. So if the interaction will break after mixing two liquids, that comes under positive. And same way you take ethyl alcohol, you mix with cyclohexane. You know cyclohexane, how it will be? This is cyclohexane, alicyclic compound. And you take acetone. What is the formula of acetone? CH3COCH3. This you treat with carbon disulfide. You know, non-polar solvent. This will not allow to form hydrogen bond. And you take another chloroform. What is the formula of chloroform? CHCl3. And this you add CCl4, carbon tetrachloride. These are all comes under what? A positive deviation. So in exam they ask you, what are the examples? Keep it in mind, key point. Where else H bond is broken? When you are adding two liquids, H bond becomes broken. That comes under positive deviation. Like ethyl alcohol mixed with water, ethyl alcohol mixed with, what is the name of this compound? Alicyclic compound, cyclohexane. This is called cyclohexane. And chloroform, this is acetone. Acetone mixed with carbon disulfide, because this carbon disulfide will break the bonds between acetone. And this is chloroform. This is mixed with carbon tetrachloride. These are all comes under what? A positive deviation from ideal. Are you following? Now observe here. Now I will show you the graph for ideal. Copied everyone up to here. Now see, for this graph I show you for ideal. Now when I am plotting graph for ideal, this is for ideal I am drawing. Previously we drawn this graph, if you remember, mole fraction taken on x-axis, vapor pressure on the y-axis. This will be P naught of A, that is vapor pressure of A component, it is decreasing, and this will be vapor pressure of B component, P naught of B. This will be decreasing, and linear sum I taught you in the previous class, this will give total vapor pressure. This is for ideal student. This will give partial pressure of A component, this will give partial pressure of B component. Whereas for positive deviation, see, dotted line indicates ideal. Now if you are taking for positive deviation, see, observe carefully, this is P naught of A, no, the same ideal I am drawing. And this is P naught of B. That means it is decreasing, and this will giving what? A total vapor pressure of the solution. Dotted line is ideal. So since it is positive, see, I am showing with a deviation. See, positive means it is deviating from ideal. See, is it deviated or not? See, yellow line is deviation. So this is for positive deviation from Raoult, from ideal. This is what solution for ideal. So in exam graphical approach also they ask which graph comes under positive, which graph comes under negative. This is ideal. This is deviation from ideal, positive deviation from Raoult. Are you following, students? So this is what ideal and non-ideal. See, for positive deviation, these are the examples you have to remember, and these are for ideal. And tomorrow class we will discuss negative deviation from Raoult's law. And in this we discussed what is ideal. In the non-ideal, we studied only positive deviation, and tomorrow we will discuss negative deviation. Clear for all? And what you do today, once you read the content till now, what I taught. Today I taught you vapor pressure of solid in liquid, and the solid is non-volatile. Thereafter I taught you what is ideal solution, what is non-ideal solution. In non-ideal, I taught you only positive deviation. Tomorrow we will discuss negative deviation, then we go into colligative properties. Okay, students? Right, I am ending the session. Tomorrow we will meet. Bye.